Hey everyone, welcome to This Explainer. Today, we're zooming in on the real unsung heroes of electronics design. I'm talking about the hidden, structural hardware that literally protects our incredibly fragile circuit boards from, well, a very not-so-gentle physical world.
I mean, think about it for a second. What actually keeps your high-tech, intricately soldered devices from just violently rattling apart when they're bolted inside a massive, vibrating engine? Even a seemingly harmless tumble off your desk can subject these tiny components to hundreds of Gs of force. The microscopic circuitry is brilliant, for sure, but it is entirely at the mercy of macroscopic forces. So the secret sauce? It lies in the highly engineered yet kinda overlooked world of physical mounting and vibration damping.
Okay, so here's our game plan for today. First, we'll look at the enemies of circuit boards. Then, snap fit versus snap lock supports. Third, adhesives and threaded standoffs. Number 4, card guides and pullers. And finally, number 5, we'll get into advanced vibration damping mounts. Let's dive right in.
Section 1. The enemies of circuit boards: vibrations, loads, and mechanical shock.
You know, even before a product leaves the factory floor, it faces some pretty intense physical threats right on the robotic assembly line. Mechanical components and machinery interactions can cause some seriously damaging misalignments. So, to understand how to protect a printed circuit board or PCB from these forces, we first need to define the exact nature of the threat. Basically, vibrations fall into two distinct categories. First up, sinusoidal vibration. This is a forced, oscillating force. It's kind of like that rhythmic, repetitive shaking you'd feel standing next to a running engine. On the flip side, we have random vibration. This is characterized by statistical probabilities of totally unpredictable severity. Think of the chaotic, jarring bumps a fragile piece of equipment endures in the back of a truck during transit. Both of these phenomena? Yeah, they lead to inaccurate component placements and catastrophic damage to sensitive electronics. But the absolute worst offender? Resonance. Every physical system inherently has a natural frequency, which is really just a specific rate at which it naturally vibrates when disturbed. Resonance occurs when an external force acting on a system perfectly matches that system's natural frequency. And when this alignment happens, watch out, the vibration's amplitude drastically increases. We're talking immense physical harm and excessive mechanical damage to the circuitry. So the primary goal of any isolation system is to suppress these unwanted vibrations by dropping the system's natural frequency way below its excitation frequency.
All right, moving on to Section 2. Snap fit versus snap lock supports, the basics of board spacing.
Now, looking at miniature nylon 6/6 support posts from the Richco catalog, we can see exactly how this works. These lightweight plastic posts are literally what hold circuit boards in place and keep them accurately spaced apart. They serve as the first, and honestly most cost-effective, line of defense against physical stress. They do this by effectively isolating the boards from the main chassis, and, of course, from one another.
The mechanical difference between these two primary types of supports is absolutely crucial to understand. A snap lock device is pushed through a hole in a panel and springs open on the other side to produce a really firm mechanical lock. But here's the kicker. To remove it, you actually have to physically squeeze or pinch the locking device. A snap fit, on the other hand, also produces a mechanical lock, but to remove it, you just pull or push, no pinching required. Engineers pick between these based on how often a board might need to be popped out for maintenance, and they use various custom spacing heights to perfectly fit whatever footprint they're working with.
Section 3. Adhesives and threaded standoffs for non-drillable and heavy-duty applications.
So sometimes you're working with a chassis where drilling a hole simply isn't an option. Maybe it's spatial constraints, or maybe it's just the material itself. That's exactly where self-adhesive supports step in, letting you secure the board purely with a high-strength adhesive backing. Pretty handy, right? Conversely, if you have a heavily loaded PC board that's going to face severe mechanical stress, a standard plastic post is just going to snap. No way around it. This is where threaded standoffs come into play. They utilize impact-modified materials and robust metal threaded inserts to bolt that board securely into place.
Section 4. Card guides and pullers, managing rack systems. Now we're shifting gears from flat, single chassis mounting to complex computer or telecommunications racks. This is where massive arrays of boards are mounted vertically, side by side. Vertical mount card guides and inserter/extractor circuit board pullers are the stars here. These mounts keep dozens of boards totally secure, but crucially, they allow for a smooth slide-in and slide-out action when a tech needs rapid access for, say, an installation, repair, or replacement.
These mechanics build perfectly on what we just talked about.
The card guides provide precision and anti-vibration security using funnel entries and tension grips that apply constant spring pressure. That holds the boards tight in the rack. But the real heavy lifting? That's done by the pullers. Large boards with tight-gripping multi-pin edge connectors need a massive amount of force to insert or extract. These pullers use a brilliant cam-type in and out action that actually provides up to a 4-to-1 mechanical leverage advantage. That leverage is absolutely vital, folks. It completely protects the fragile circuitry and those sensitive connectors from snapping under undue physical stress.
Okay, Section 5. Advanced Vibration Damping Mounts, Elastomers and Silicone Gels.
So, the crucial point here is understanding how passive vibration isolation actually works at this advanced, extreme environment level. Honestly, the best way to grasp this is through a car suspension analogy. It's totally relatable. A passive isolation system consists of two main parts. First, you've got the elastic element. Think of this like the coil springs in your car, or specialized rubber quiet mounts for a PCB. This softens the incoming vibration. Second, you have the damper. This is like the shock absorbers in your car, or a special liquid or gel inside an electronic mount. The damper actively absorbs that vibrational energy and safely dissipates it.
Which leads us directly to incredibly advanced, specialized materials like Gelmex silicone gels. Let me tell you, these are definitely not your average pieces of rubber. Because of their incredibly unique molecular structure, these gels disperse physical impact three-dimensionally. They are literally ideal for fragile PCBs that might otherwise flex and crack in harsh, heavily vibrating environments. And it gets better, they dampen a remarkably wide frequency range and emit very little siloxane gas. That makes them incredibly safe and stable for enclosed, highly sensitive electronics, a real game changer.
Just look at the incredible scaling of these AGEL vibration damping capacities. To put this into perspective, we go from tiny bush-type gel mounts, designed to isolate a lightweight component weighing a mere fraction of a kilogram, around 0.2 kilograms, all the way up to massive insulator mounts. Those big ones are capable of damping vibrations for enormous, heavily loaded industrial equipment weighing up to 300 kilograms. The engineering scales dramatically, but the foundational physics of that silicone gel damping, it remains beautifully consistent across the board.
So why does all this matter to us? Well, because these unseen structural components are literally what keep the modern world running securely. These advanced isolation mounts are utilized in incredibly high-stakes applications. We're talking rugged military and defense systems, the aerospace industry, our global telecommunications networks, heavy-duty oil, gas, and energy sectors, and even critical transit protection and mass transportation. Seriously, without these highly specific vibration dampers, our global infrastructure would literally rattle itself to pieces.
Which leaves us with a fascinating, provocative question to consider. As we continue to design the flexible, biological, or even microscopic printed circuit boards of tomorrow, how will our mechanical mounting hardware evolve to protect them? The unseen world of physical engineering is always going to have to keep pace with the electronic innovations it shields. Thank you so much for joining me for this explainer. Keep wondering and keep learning.